Okay, today we have to discuss about the Helmholtz Galavanometer. Okay, Helmholtz Galavanometer is mainly working on the principle of the tangent galvanometer. Okay, the difference between Helmholtz Galavanometer and tangent galvanometer: Helmholtz Galavanometer having the two circular coils carrying a current, but in the tangent galvanometer a single coil carrying a current. Okay, here in the Helmholtz Galavanometer we have to consider the two circular coils. In between these two circular coils you have to keep the compass box, okay, or magnetic needle. This one, the compass box containing a magnetic needle, you have to keep in between the two current carrying coils. Okay, so this here the main principle of this Helmholtz Galavanometer is you have to prove that x equal to a by 2, means the distance between the center of the coil x, the distance between the center of the coil is equal to the radius of the either coil. Okay, so you have to prove that radius of the either coil. This is the main principle of Helmholtz Galavanometer. Here we have to prove. Okay, so the magnetic needle in the compass box which is placed in between the two coils, okay, and similar to the we have to mounted on the these two coils, we have to mounted on the one base. Okay, we have to mounted on the base. The distance between the center of the coil is equal to the radius of the either coil. The magnetic field at the center of the needle, the magnetic field at the center of the needle due to the current passing through both the coils in the direction. Okay, here the two coils, okay, the C1 and C2 are the planes of the two coils. C1 and C2 are the planes of the two coils, and these two coils carrying a current I and having the radius A, and the distance between the center of the point is x. You have to take. It is the setup of the Helmholtz Galavanometer. Okay, and now we have to show that O1 and O2 are the center of the two coils. When you take O1 near to the O2, at that time the magnetic field of C1 will be decreases and C2 will be increases. And now we have to make a setup when the equal amount of magnetic field of one coil decreases and the equal amount of magnetic field of second coil will be increases. We have to make the arrangement in this, and it means you have to maintain the uniform magnetic field of along the axis, and we got the resultant magnetic field here. So you maintain the uniform magnetic field along the axis of the coil, center of the axis of the coils. At that time the deflection, the uniform deflection will be takes place inside the compass box. The compass needle will be uniformly deflected because the two coils carrying a current in the same directions. Okay, it is also having in the same direction, it is also carrying a current in the same directions, and the distance between the coil is equal to the radius of the either coil. This is the main principle we have to prove here. Okay, when it shows the uniform magnetic field, when this compass shows the uniform magnetic field, at that time you know that the current carrying loop having a magnetic field formula. Okay, so you have to take that one. Here the magnetic field at a point on the axis of the circular coil. So the magnetic field at a point on the axis of the circular coil, you have to take it as B equal to mu naught N I A square divided by 2 A square plus X square whole raised to 3 by 2, equation 1. We have to derive this expression in the last session. Okay, so if the magnetic field on the lines, okay, if the magnetic field on the lines O1 O2 is to be uniform, so magnetic field in the lines, it means O1 O2. Okay, magnetic field in the lines is uniform. So at that time So delta b divided by delta x must be constant, means it means the magnetic field at any point must be constant. Or you have to take another point, d square b divided by d x square equal to 0. It is also a constant. Sorry, dB by dx at any point is constant, and again you have to differentiate this term, you will get the 0 equal to 0. Here n is the number of turns of each coil, and A is the radius of the coil, I is the intensity of the current you have to take, and x is the distance between the either coil. These are the written here. And differentiating equation number 1 with respect to x. Okay, so here equation number 1 is there here, and you have to differentiate this term with respect to x. Okay, then differentiate that above equation. So the b is dB by dx equal to mu naught divided by 2. So you have to take mu naught divided by 2 as a constant outside, and ni a square is also constant. These are the constant term you have to take outside, and this is the differentiation of 1 by a square plus x square whole raised to 3 by 2. Okay, it is in the form of 1 by x. Okay, 1 by x differentiation, you have to take x minus 1. So d by dx of x minus 1. So next differentiation of x minus 1 is, you have to take it as minus 1 x raised to n minus 1. Okay, so you have to differentiate this 1 by a square plus x square whole raised to 3 by 2. It is in the form. Okay, then here minus 3 by 2 mu naught n I a square, you have to take it as a constant, and here a square plus x square minus 5 by 2 into x. So you got the differentiation of this term. So 3 by 2. So it is, you have to take it as minus 3 by 2, because you have to take the differentiation of x raised to minus 1. Minus 3 by 2 whole raised to minus 5 by 2. So here with respect to x, you are doing x square into 2x you got. So equal to minus 3 by 2. So take a common minus 3 by 2, and these two will be cancelled. So remaining term here minus 3 by 2 outside, mu naught n I a square. So a square plus x square whole raised to minus 5 by 2 into remaining term x. Next again you have to differentiate above equation with respect to x, this equation. Okay, so dB divided by dx, so differentiation d square b divided by dx square equal to, so minus 3 by 2 mu naught n I a square is a constant term, or to take as it is, and the differentiation of this term. So a square plus x square minus 5 by 2 plus, so minus 5 by 2 a square plus x square, and minus 5 by 2 minus 1. So 2 ones are 2, minus 2 minus 5 is minus 7 by 2 into 2x square. Okay, so next these two will be cancelled here. So remaining minus 3 by 2 mu naught n I a square plus x square whole raised to minus 7 by 2 a square plus x square. So here you have to take the common minus 3 by, here you have to take the common on this term is a square plus x square minus 7 by 2. So ಇಲ್ಲಿ minus 7 by 2 a square plus x square minus 7 by 2 ಮಾಡಿದ್ರೆ, ಸೊ ಏನು ಉಳಿತೈತಿ ಇಲ್ಲಿ, ಸೊ ಪ್ಲಸ್ 1 ಉಳಿತೈತಿ. ಸೊ a square plus x square in this term, and ಇಲ್ಲಿ ಈ ಟರ್ಮ್ ಕಾಮನ್ ತೊಗೊಂಡ್ರಿ. ಸೊ minus 5 by 2 here 2 cancelled, so minus 5 x square remaining term. So equal to 3 by 2 mu naught n I a square plus x square whole raised to minus 7 by 2, and here minus 5x square is minus 4x square plus a square. So for the calculation purpose you have to reassign the signs. So 4x square minus a square here we got. So as we know that this is the second differentiation, so initially we discussed that the second differentiation d square b divided by dx square equal to 0. So next you have to take 3 by 2 this term as it is, okay, equal to 0 because d square b divided by dx square equal to 0, or 4 this term comes here, at that time this whole term will be 0. So remaining term 4x square minus a square, 4x square minus a square equal to 0. So x square equal to minus a square comes here, the plus a square divided by 4, x equal to a by 2. Okay, this is the condition. So we obtain uniform magnetic field. The magnetic needle must be at distance a by 2 from center of the coil. Okay, central distance between the two coil is equal to the radius of either coil. This is the our satisfied condition of the Helmohtz Galavanometer. It means